So this part is about CUDA. So the first question is, how many people already program in CUDA here? Okay, there are some. Okay, so you can check the quality of my lecture. All right. Essentially, CUDA as a concept of Compute Unified Device Architecture is a set of hardware and threading runtime concept to work with massive parallelism, where CUDA C, or actually it's not C, but C++, is a language, is an extension to the C++ that is extended with specific constructs to provide CUDA support. This is, I guess, the most popular language so far, but there are other CUDA-aware languages. For instance, CUDA Fortran, and in CUDA Fortran will be the next lecture today. So in terms of hardware, CUDA focuses on massive parallelism. Word massive here means that we escape from the world of 4 or 8 cores and instead considering the architecture with thousands of cores. To fit this thousands of cores, we need thousands of parallel threads. These parallel threads are not completely independent, but they rather are also grouped into blocks, and smaller blocks called warps. So here is the picture. Threads of each block can share some fast memory called shared memory. Don't confuse shared memory with global DRAM, because shared memory can work on the speed of almost on the speed of registers, which helps, for instance, to accelerate matrix multiplication on GPUs to impressive numbers. So shared memory is shared between blocks of threads. But there is a smaller blocks inside blocks of threads. They are called warps. Warps are subgroups of threads in block that are executed synchronously. So if we depict all these points here, we will see that in general we have a flow of threads that are executed on a single GPU. This flow of thread is first decomposed into blocks, where each block has warps, and each warp has threads. As you see, synchronous here, in terms of if vertical scale is time, synchronous are only warps. Blocks can run asynchronously, which is actually a huge difference in comparison to traditional multi-core, where everything runs simultaneously, which is explained in the next point. SIMD, single instruction, multiple threads. SIMD was introduced by NVIDIA to distinguish this synchronous and asynchronous parallel model with SIMD, with D for data, where we have one thread performing the same operation on multiple data points. So this is the GPU architecture and CUDA concept in a nutshell. We have threads. We have thousands of threads, and not all of them are running simultaneously from the hardware point of view. But in terms of programming model, they are the same threads as we are comfortable with in multi-core world. Okay, so I suppose, although there are people here who never worked with CUDA, I think many of you already are working with MPI and OpenMP, right? So if you have experience with MPI and OpenMP, it's very easy to understand CUDA. I will do the following comparison. So on the left, we have a cluster like PICDENT, for instance. Your MPI plus OpenMP application should look like this. The process, so the largest square is application. So the small one is process, and the thread is one thread inside each process. In comparison to this, what we have in case of GPU, instead of application, we have a CUDA kernel, a program that will completely run on GPU. The smaller block is block of threads. The smaller groups inside block are warps, and this is the thread inside warp. So technically, it's the same kind of topology. You have something like MPI. You have something like OpenMP embedded into something like MPI. In case of GPUs. So in fact, CUDA GPU is like a cluster in microscale, packed into a very small box, and also equipped with a CUDA programming model, which better suits the massive parallelism concept. To introduce you the basic CUDA language constructs, here I have the comparison of MPI and OpenMP topology functions with CUDA. So let's look into this program. On the left, we have an MPI plus OpenMP code, which is simply requesting the MPI rank, and each MPI rank then enumerates all OpenMP threads it has inside this process. So for the process rank in MPI program, we have MPI comp rank, and a close equivalent of this in the GPU program will be block index. Rank is always linear. We can enable a multi-dimensional topology in MPI, right? But by default, it's linear. And contrary to this, in CUDA, block index is offered to be one-dimensional, two-dimensional, three-dimensional. So if you want it to be just linear, you put .x. Or optionally, you can use second and third dimension will be .y and .z. Similar to this, comp size will be grid dimension, also with x. And here we are spanning the OpenMP parallel section and getting the thread index and the total number of threads. Equivalent of this in CUDA will be thread index, also x, and block dimension, block dim, also x. So what we will have if we will run this program with two threads and two processes, there will be some hello kind output from every thread of every process. And in case of GPU, this program is supposed to be run on GPU, but GPU is not a fully independent device. We can't deploy the GPU directly. We need a host program. We need a program that will run on CPU as a driver, that will have a special function call, and this function call will call this actual kernel. So this is the simplest driver, just the main entry with GPU kernel here, which refers to the name of the kernel with a special annotation global, which is saying that this is a global kernel on GPU. 2 is the size of grid, number of blocks. And second 2 is the number of threads in block. So we are forwarding this configuration somewhere inside the CUDA runtime. And the CUDA runtime knows that these 2 and 2 should be projected onto this grid dimension and block dimension. It is always a good thing to check the error status of the kernel in case there will be some problem. And the CUDA device synchronize is saying that we want to wait for this function to be completed. Because by default, the CUDA kernels are executed asynchronously. This is very handy, by the way, because you can, for instance, have combined CPU plus GPU computations. Then you start a GPU kernel, and in the meantime, you can also deploy something else on CPU and then synchronize. So here we just synchronize. And and this CUDA error check is a macro to check the error status. I'll show you how it looks like a bit later. And surprisingly, we can get the same output from the simple GPU program. So this is really a lot of common here. Okay, so we already had this chart in the first presentation. And the main idea here is that GPU has its own RAM. And the most efficient approach to program GPU is to keep the data in this local GPU RAM. Currently, CUDA developer has to allocate GPU RAM explicitly and copy input data before calling kernel and copying output data after calling kernel. This is actually not necessary. There are alternative approaches how you can map the host memory directly to GPU. But this is an advanced topic. We are not covering it in this presentation. So let's assume that CUDA developer has to allocate GPU RAM and copy memory. So in this case, we have a program here which specifies the number of threads and number of blocks. When we allocate the CPU memory buffer, when we allocate the GPU memory buffer, when we are calling kernel, which fills the GPU data array with some output data. And after kernel finishes, we copy back the GPU data to the host data to be able to read it from CPU. And then free GPU memory and read the data that has been written on GPU side. On last GTC, which is currently GPU technology conference being held in San Jose, NVIDIA presented an NVLink technology that will allow fast direct access from GPU to host memory in several years. So it just has been announced, and it will also allow you to get rid of this explicit copying. But there are still other ways to get rid of this explicit copying for some performance penalty, of course. So in terms of efficiency, this is the best way. Here on the left, we have a host program, and here's on the right, we have a host program, and on the left, we have kernel. This is, as I promised, the macro which checks the error status, which is always a good thing to know the error where it happened. Coordinates here is a int4 vector where we simply store the topology, the indices of the current thread on GPU. And here we are writing this vector into the output array. So this output array is written on the GPU side, and when we copied it to the host memory buffer, it will be available to the host system. Compilation runs simply. We need the CUDA-enabled compiler and VCC, optimization option, and source file name, output file, and just run this output file. Okay, so we just wrote our first CUDA program, even two different CUDA programs. As we see, CUDA uses two-level compute grid topology similar to MPI plus OpenMP. CUDA topology, however, has a flexibility to be 1D, 2D, or 3D at your option. CUDA kernel can't be a standalone program, and needs a driver program, a host application to be called from. During the kernel startup, blocks of threads are created, and no OpenMP like Pragma 4 or anything is required. Everything in CUDA, everything is done implicitly. CUDA kernel launch is asynchronous and could be synchronized asynchronously with this, explicitly with the call, or implicitly. There is another way by using if you just use the data that was a kernel parameter. For example, here we called kernel, and we don't need a CUDA device synchronized here because we'll be copying data which was just written by kernel to the output array. So this is an implicit synchronization. GPU has on board DRAM, which is independent from host, and data between with memory has to be transferred somehow, explicitly or implicitly. It is always a good idea to check the error status of every CUDA call. Surprisingly, we have a lot of students that ignore this recommendation and have a lot of trouble in their when they are just starting their learning process. Okay, so let's go. That was a mini conclusion, and let's get a little bit forward. CUDA compute grid supports 1 of 3 dimensions. So 1 to 3 dimensions. So here is an example of one-dimensional setup. Here is an example of two-dimensional setup. This will be like depicted here. And instead of plain numbers, we use a structure, dim3, where the third position here is field 1, as we are going to have 2D. And the three-dimensional setup is a all position field here. It will be 16 by 8 by 4 in 3D for dimensions of blocks grid. And in every block, we will have 8 by 4 by 2 coordinates of threads. Why CUDA introduced this right into the programming model? Because having the multidimensional indexing by default is a very handy thing. For porting multidimensional loops into GPU kernels. For instance, here we have the original CPU loop on the left and the equivalent GPU program on the right. So you see here are the headers of loop. In case of GPU, we have the kernel. We have the kernel with the same body, data IDX is IDX as here, but no more loop headers here, because loop headers are gone. They are inside the CUDA runtime. We only specify the indices ranges of these original loops. And the synthesis ranges are going to the launch bounds of kernel here. Ranges are distributed between threads and blocks of threads, and blocks number is rounded to handle the remainder. So as we have some block size, and it could be not the exact divisible of our actual dimensions, we need a round up here. And the max, and the max here means that we need at least one block of threads. Otherwise, this kernel will never run. Or actually, there will be an error to run a kernel with 0 blocks. Okay, so this is the typical scenario, by the way, how you can port a CPU loop into the GPU kernel. But it's simple, but sometimes it's not enough. The thing is that on different kinds of GPUs, there are limitations on the maximum possible values of block dimensions, block sizes, block grid dimensions, and block grid sizes. So what if our ranges in our loop are larger than the maximum allowed dimensions that we can put here? The obvious solution would be just to process multiple grid points in one GPU thread, which means that the loop headers return here, they are back, but in the other form, we need to pass the increment, the non-unit increment here to iterate several grid points in a single GPU thread. So in order to do this, we compute these increments, and the maximum kernel launch grid limits could be queried with this call from for instance, this is the index of GPU here from the GPU number 0. You might be wondering, why are not we process consecutive grid points in a single thread? Why we are jumping here, jumping with large stepping? This is because of the coalescing, that important optimization that I mentioned in the first lecture. If we read the role from, we try to read columns from individual threads, our GPU efficiency turns to be a disaster. That's why we need a single warp of threads to share the consecutive buffer. Then we jump by the size of the buffer to the next buffer, and this next buffer will be again shared between threads of the same warp. Okay, so this is again the general approach. That you can reuse this as a SNP-net for your stencil codes, for instance. And I have one production example which is not doing the useless data store, but instead doing something, some meaningful computation. The wave equation stencil here, and in case of Xeon CPU with OpenMP, there is also OpenMP here for this version. We have this compute time, and in case of cheap laptop graphics like similar to this laptop, we have more than 2 times less compute time, but we also have the latency for data stores and for host GPU data loads and storing back the results. And there is also a latency for allocating the GPU buffers and deallocating them. So, but even if you it's okay. Even if we add all together all these numbers, there will be, as you see, there will be less than CPU timing. But it will be as the porting of your application progresses, it will be it will be always a good idea to keep the data you are going to reuse on GPU, to keep it on GPU, not to load and save it multiple times. Okay, so for the introductory part, we can talk a little bit about simple optimizations. So the essential thing is to do the coalesced memory accesses. This is the most essential thing to have impressive GPU speedups. A popular problem for newbies is what should be the block size, because you have a degree of freedom. You can set up any numbers there, in fact. So if you have no idea, you can start with this block configuration, and it should be almost optimal for most of the cases on the modern GPUs. Compilers CUDA compiler can tune code for a particular GPU identified by compute capability. This is kind of GPU family and revision number. And depending on this exact compute capability, it might be able to optimize the code further. For instance, if you are doing sort by K, one of my benchmark examples, without this option or with option for kernel, the difference will be the factor of 2. So specializing for Kepler in this case will be of course better. And it's always a good thing to learn the new programming model with some handy and comfortable environment. This is to show you that this programming environments exist for CUDA. This is the window of Eclipse, where you have both CUDA and C++ code highlighting. You have embedded profiler and embedded debugger. Probably the best scenario is to use this as for software with large code base, or for GPU, workstation, or laptop. Another possibility would be gedit of Linux, which will allow you to directly edit remote files on cluster. And by saving these files, you are saving them on the remote file system. And here, in the bottom, you can also have the remote console to immediately test what you are coding here, or for instance on the PeakDyn node. Okay, so as a conclusion, I hope that I convinced you that CUDA is very easy, especially if you already worked with MPI and OpenMP. The general existing code porting strategy would be to extract loop body into the global function, which is GPU kernel, replace the original loop with kernel launch, where the launch bounds will be equivalent to our loop ranges. Next, we need to transfer input data to GPU before and transfer the output data after kernel launch. And the easiest thing would be to switch the compiler from C++, what you had, to NVCC and rebuild your program. Development environments are already available for CUDA and should make everything comfortable. And there are, of course, this tutorial is pretty much enough to start coding in CUDA and have impressive speedups. But there are still several things beyond this tutorial, which are shared memory, streams and asynchronous data transfers, debugging profilers, and most importantly, some practical test cases. So for all these extended topics, we again invite you to apply for academic or commercial training courses. Thank you.